So with this, I suggest that the first presentation will be made by Dane. And let's try to write down as much as possible in form of written comments and give them to the authors, because we cannot be too much over time while listening and addressing. Okay.
I'll have to share this screen so they can see it.
Oh, you cannot see the screen? Good. So it is what is going on.
Okay. Okay, so I'm just going to start out. One of the questions last week that I talked about was going to be addressed this week, and that's what we're going into. So the question, more of a statement, says, surely there are some experimental studies that are relevant and could be quoted. This is actually a computational study, not an experimental study, but we're going to go into it because it got the same results. So the top equation that you see there, equation 11, it says that this reaction pathway is pretty much a dead end when the question of formation of water is at hand. So now, I guess, from the literature, understand that there is another pathway that could take place resulting in OH rather than H2O, and perhaps that could be used as a reactant, or maybe it's a reverse reaction before going forward to the formation of water. Yes.
So where this reaction is coming from?
This is coming from...
Not the name of the author. Which experimental method allows to find this?
This is a computational study.
Okay.
Yep. And then from the same paper, this is the reaction mechanism that I found. So it aligns perfectly. Formation of water, we know computationally has been proven to exist. And this is the extent of the mechanism that they have computationally. There wasn't any like molecule visualization showing how they reacted or anything.
So it was not dynamics. It was optimization of transition state.
Yeah. So here's an experimental study. These two equations were the only two in the paper that I found that had water as a product. So it's been proven experimentally that water is in fact a product. So that's good to know. However, the mechanism for an H2O molecule to form still wasn't ever outlined in any of the literature that I found. So there wasn't a specific, step-by-step mechanism of what occurs. I think that's important to note because that's one thing that was outlined in my manuscript.
But again, what is the experiment?
So this
just outline it for those who
okay.
never seen it.
So this experiment, they took they took more than two forms of a nitrogen and oxygen mixture or molecule, nitrogen and oxygen containing molecule, and use it as the oxidizer for hydrazine to see what the reaction would be. And the top, actually both of these ones listed here were explosive combustions, whereas another one that had, I should have put it on here, I wish I remembered it now, I believe they used hydrogenyl radical and then put in nitrogen monoxide, and it wasn't a combustible reaction, so they just kind of writ it off as not usable for rocket fuel, which is what the study was worried about, was the use of combustibles, hypergolic fuel. So we know that water exists, it's been proven.
Not clear, still not clear.
Not clear. Yes?
So not clear about how to characterize products. How in this experiment one finds the proportions, the molar fractions of the products.
Yeah, that That wasn't. I mean, maybe I looked, or maybe I overlooked it, but I didn't see anything like that they were doing NMR or mass spec in the paper that I'd read. But I would have to imagine that they had to have done something like that.
Okay.
I mean, experimentally, you'd have to determine the products one way or another, which.
Not just products, but their amount.
Yeah, yeah.
Okay.
So I'll look into that and find if what method they use to quantify. All right, so that's pretty much it for the literature review. We're going to move on to the ACS talk now.
They can be integrated. You can first declare your goals and title, and then before you go to methodology, briefly overview literature.
Okay. All right, so we'll talk about hydrogen combustion again today. So we could see this rocket take off, and this is hypergolic fuel. Again, not muted. I need to figure out how to do that. So this is hypergolic fuel. You don't see a lot of residue coming off the rocket itself. Normally with cryogenic, it looks like there's an ocean of ice falling off of it, which is pretty much exactly what it is. You don't get that with hypergolic fuel. So what we're going to talk about today, we'll explain what hypergolic fuel is, talk about some methods and why we're researching hypergolic fuel, specifically the reaction of hydrazine and dinitrogen tetroxide, which is commonly used in rocket fuel. So then we'll talk about the predicted and observed reactions that occur, talk about what's exothermic and endothermic in question of the reaction, some stability factors, and then we're going to go even further on the stability factors today and talk about proof that those stability factors exist, which specifically in this presentation is going to be water. And then we'll wrap it up with conclusions. So hypergolic fuel is when you mix two reactants together, a reactant and an oxidizer, you're getting a spontaneous combustion which occurs. And if you look on the right-hand side of the screen, you can see this occurring. A dropper will come in and drop 1 drop of oxidizer into hydrazine, which is the dinitrogen tetroxide, and you get a combustion instantly. Now that's hypergolic fuel. It's ideal for maneuvering spacecraft because you can do small bursts. It's a lot more controllable than other forms of fuel. However, it's highly toxic, so it's not used in manned spacecraft just for the risks that it poses to humans. However, if we can get past this toxicity problem, it does have the highest level of specific impulse, meaning that you get the most bang for each pound. Yeah, and it's got a high freezing point in comparison to cryogenic fuel. So on a spacecraft, onboard spacecraft, you don't have to have as many parts making sure that this doesn't, that the fuel doesn't freeze. So methods, the electronic structure at each position was determined by DFT via VASP software. We could see the Hamiltonian here, which, you got a question?
Yeah.
What's up?
Why methods? What is the goal? What is not clear?
So
can we be happy without this research?
Yes. Okay. So the purpose of this research would be to maximize the amount of water molecules formed in a given ratio of fuel to oxidizer to improve stability and in turn reduce toxic byproducts. Therefore, it would be usable in manned spacecraft and it would save money for space exploration programs. In order to do this, though, we need to determine the mechanism for the formation of water, which currently isn't outlined in the literature that I've read. However, it is known that water is formed, just the reaction that takes place in forming this isn't detailed. So that's what's going to be determined, and this will be determined using ab initio molecular dynamics. So that the bottom left equation we could see here is the kinetic energy, and on the right we just see Newton's second law there. for the top equation, the Hamiltonian specifically takes into account the coordinates of each molecule. Does that satisfy?
No one objects?
John?
Well, I would agree that the coordinates are taken into account when calculating the density, but they're not explicitly listed within the equation because you have small r, which is electron density, whereas the big R in the bottom of the equation correspond to actual composition. So the electron density in the top equation is dependent on atomic coordinates, but isn't explicitly listed in the top equation.
Okay, but the coordinates are an output of the VASP software, correct?
In the self-iteration for each electronic step, the ions can get moved a little bit, but the main output from VASP is the electron density and then the relative total energies. And so the energies and the orbitals on the right-hand side of the equation.
Okay.
So yes, you can get them as the optimized locations as the output, but the main thing that we're interested in is the electronic portions.
Okay. Okay. I'm going to look more into that, and we're going to keep moving forward as soon as we have a lot of stuff to do. So the simulated mass spec was obtained using this formula. It takes the positions in respect to time of different molecules, and molecules are defined here as closely grouped clusters of atoms. So we don't necessarily know for a fact that some of these molecules indeed exist, but they're within a reasonable interatomic distance of each other that we can assume them to be one molecule. Yes?
No question about your understanding, just question how to present it. The junction between previous slide and this one, what is the output of the previous slide? What is generated during your molecular dynamics? Just tell it in a highlighted form.
We get the coordinates as well as the velocities.
As function of
time.
Yes, do not hide it because other literature sources do not do it. You are unique because you find them as function of time.
Okay. All right.
Please keep that.
So there's three types of hydrazine that are used in rocket fuel: hydrazine, monomethylhydrazine, and UDMH, unsymmetrical dimethylhydrazine. The one used in this research is hydrazine due to its high performance, it's got really good performance. That would be its pro. Its con would be it has a high freezing point, which obviously lower freezing point would be better in space. Then it requires less parts keeping it at a certain temperature. Monomethylhydrazine has a better performance strictly due to a lower freezing point. So the word performance isn't defined as necessarily having more thrust or more energy output even. It's more so just it has a low freezing point, so it's better, saves money in that aspect alone. So UDMH has the lowest freezing point, so obviously that's a huge pro, but it is the least efficient, so not the best. So that's why hydrazine was picked for this research. This research specifically, we use these parameters intentionally, 3,500 Kelvin, and the volume is significantly small because it increases the chance of interactions occurring. Yes, is that Yulun?
Adam.
Adam?
So you were talking about how the different fuels were liked for their freezing points being lower, or have more energy per gram. Have they looked at possibly combinations of these fuels for trying to do freezing point depression kind of stuff?
Yep, absolutely. The most commonly used ratio right now is 50% hydrazine and 50% UDMH for the fuel, and then they just use the dinitrogen tetroxide for the oxidizer. However, my understanding from the research that I've done is that 50-50 ratio isn't necessarily proven to be the best ratio. So that's something that is to be looked into also. Perhaps a 30-70 ratio would be better, 40-60, who knows. That needs to be researched more in depth to answer that.
Okay. Excellent. Thank you.
Yep. Thank you for the question. So, again, back to the reaction. It's a 1-to-1 ratio of hydrazine and dinitrogen tetroxide molecules. Again, the high temperature is to speed up this process so that we can visualize it more. It's not expected that these parameters should affect the reaction pathway, but it is a possibility that should be considered. So all right, this is a new slide. So the complete reaction that you see at the top here is just the two in the red below it combined. It's to help understand the formation of the diazine molecule, which we'll talk about more in depth in the next few slides. But you can see the hydrazine becomes unstable when it's in the presence of heat. When it loses those 2 electrons, it naturally loses 2 protons and becomes a diazine molecule. So we'll go into the 3 most important reactions here that occur, in my opinion, leading to the formation of water. So this first reaction, if you look on the top left, you can see a predicted reaction mechanism where you watch the dinitrogen tetroxide come within a close proximity of a proton, and then a nitrous acid is formed and leaves a nitrogen dioxide, nitric oxide, yeah. So that was predicted. We could see the observed in the top right. This was gathered through JMOL using FAST. You see the hydrogen atom attaches there. So the 2 nitrogens in the middle here, you don't see them bonded right now, and that's because the software used doesn't represent those bonds if they're outside of a certain distance of each other. But you can see again the hydrogen atom comes in and attaches, and then that bond breaks there, and you're left with nitrous acid. On the bottom, you can see this more clearly, how this happens. Hydrogen 5 comes in. It's a fairly short reaction. It's only 11 femtoseconds long, and it leaves us with the nitrous acid, and then NO2, which can later be hydrogenated into a nitrous acid as well. The second reaction, most important, one of the most important, on the right hand, if we look on the top left of the predicted reaction mechanism, on the left side you see the diazine molecule, and on the right side you see a hydrazine molecule. And when they come within close proximity of each other, they become 2 hydrazine radicals by losing a hydrogen atom from one of those. And if we watch the observed reaction, we can see this to be true. It's quick. You can see the hydrogen bonds there, and then eventually loses, and you're left with N2H3 twice. Again, on the bottom, the 3 panels, this is the fastest of all of the reactions. It's only 5 femtoseconds long. Happens fairly quick. And the third most important, in my opinion, is the formation of water. So using the products of the last 2 reactions, we see the nitrous acid come within close proximity of the hydrazine radical. It bonds with an oxygen, loses an NO molecule, and then the water leaves. The nitric oxide, diazine, and water are our products there. We can see this again in the observed reaction mechanism. Again, this is fairly quick, and we're left with the formation of water. You can see in the middle of the screen there with the 1 red and 2 white 4 panels on the bottom outline this and the bonding of all the atoms and how they break off. If we look at 92 femtoseconds there, you can see the nitric oxide leave, and then at 104 femtoseconds, the water molecule leaves. Now, the question is this water molecule truly a water molecule? And this is going to be proved through electron density. So if we look at our total charge, we're going to go in depth here. I'll probably change up how I explain this, but we have 4 panels on the bottom, and we're going to go through these next 4 slides, correlate to each one of these frames. So the first one, at 89 femtoseconds, you can see the nitrous acid on the left here. Again, on the right-hand side, you see it. It's partially hidden there. There's no bonding between the nitrous acid and the hydrazino radical at this point. At time step 91, you can see that bond forms there, and the hydrogen is now attached to that oxygen molecule on the nitrous acid. And then that bond breaks, we'll lose the nitric oxide, and at time step 104, we can watch the water molecule separate. And at this point, my understanding is that I need to change my ISO values to a lower amount so that the higher amount. So
higher ISO value, smaller diameter of the cloud.
Okay. So these clouds need to be readjusted. As of right now, I think that these clouds prove that it is a water molecule, just judging by the changes of the cloud formation itself. However, I think that it could be more visually appealing. So on this top left one here, we see a diagram of distance and energy versus time. The total energy of the reaction is in the green line there, and we can see if we were to draw a line of best fit, it's got a negative slope, which correlates with an exothermic reaction. The red line is the distance between oxygen 35 and hydrogen 8, which is 2 of the atoms in the water molecule we just described in detail on the formation of. And then the blue line is the nitrogen 23 and hydrogen 8, where that hydrogen is donated from that nitrogen. And if we zoom in on that top graph, we can see the bottom graph here, and we can see as the red line approaches 1 angstrom, the formation of water occurs, and at our time step 104, we can even see an increase in total energy, meaning that the formation of water is endothermic. So that's why water is claimed to be a stability factor in this reaction. It's the largest contributor to stability, and we can see again the next spike in total energy happens at 114 femtoseconds, which is when our second water molecule is formed. And then our third and last in this reaction will occur at 335 femtoseconds, which is roughly that last spike in total energy. It's the largest spike. So it's assumed that maximum stability has been reached at this point, and now the reaction will continue outputting energy as an exothermic reaction. And then the top right is just a screenshot from the final step of our reaction. You can see the 3 water molecules are circled. There was only 3 formed in this 1-to-1 ratio of 4:4. So conclusion, reaction mechanism was determined for a 1-to-1 ratio using molecular dynamics and VAF software. Trajectory was determined by solving Newton's second law, and not in here, again, I forgot, a mass spec was obtained to prove the occurrences of different molecules throughout the reaction. And that will be discussed next week more in depth. I'll remember to put that in my references, and I'll take any questions.
Okay, let's thank Dane for interesting presentation, and Are there any questions?
No questions here, Dr. Killen.
Okay, thank you.
But we did have a comment that we are scheduled till 7. However, we have a tornado-producing storm heading our way about that time, so we might need to pull out a little sooner than that.
Okay, yeah, let's speed up. If we will be interrupted, I don't know what to do. So let's do those who are in the room, and if Sam will not show up, we'll finish earlier. More questions to Dane? Okay, Dane, please collect written comments. When you will be working on the next version, start from the conclusions.
Okay.
Make as much as possible for the conclusion, because people remember only the first and last thing.
Okay.
John, you had...
No, I just had one quick comment.
What's up?
Like on a few of your first slides where you're showing equations,
Yep.
I would suggest to rewrite them in the PowerPoint equation maker rather than the screenshots from wherever you took them from.
Okay.
And with the mass spec equation, I mean, it'll probably be shortened. It won't need to be 2 lines once you rewrite it.
Right.
And you could always put in, snapshots of a number of different molecules, and that way you have a visual to say, at this time point, we're looking at the possibility of all these different combinations, just in case it would help.
Okay.
So.
All right. Thank you.
Okay, let's thank Dane once again. Aaron, would you like to go forward? Sure. Will you be able to find your...
Is it just on the desktop?
Yes. If you just go to PowerPoint and look for already opened.
Oh, you mean this icon?
Yeah. Good. Please go forward.
Oh, okay. So, oh yeah, that camera going. So today I'll be talking about the case study of dye-sensitized lead halide perovskite solar cells and the influence of the dye morphology on hole transfer. So explicitly, we're looking at spatial locality versus explicit ligand coordination. So maybe simply more put, it could be thought of as through space through bond charge transfer. So to begin with, we'll just look at a summary of the work that we'll be going through for the next 20 minutes or so. So basically the results that we found is that for the dye molecule that we modeled, that through bond charge transfer is much quicker than through space charge transfer. So we have 2 models. So where we have a bond or a dye molecule that is just close to the perovskite surface when we model hole transfer through. And then we also have a model where the dye molecule with methoxy linker groups, which are represented as the little red arrow or lines between the perovskite and the dye. And like I said, that the charge transfer rate through bond is quicker than through space. So next we'll look more in depth at the atomistic models that we use to compute the charge transfer rates. So to begin with, so overall we looked at many different dimensionalities of perovskites. So we have a perovskite quantum dye, which is still computing and won't be presented. We also looked at perovskite nanowire and thin film, where each dimensionality provides its own unique benefits. So with decreasing dimensionality, you'll have increased interfacial surface area and also increased surface coupling with reduced dimensionality. So I guess I'm not sure where to trail off with that, but so for thin film, we'll have increased surface area compared to bulk with a little bit of increased coupling. And then nanowire, you'd expect greater coupling. And you also get the benefits of controlled charge transport for when you're trying to transport the hole through the material. But for this presentation, we'll just focus on the thin film model. So the dye models that we use, so a popular hole transfer material in perovskite-based solar cells is spiromutad, which is shown to be the most efficient hole transfer material. and it's a rather large organic molecule. So instead of modeling the whole molecule itself to save computational time, we made an approximation where we only look at a chunk of the spiroamidotad. So it's basically like 1/4 of a segment of the entire molecule, which we assume that will provide the same interfacial dynamics between the perovskite and the dye molecule. And we also do a control experiment where we look at a dye molecule without the methoxy linked groups to model the through-space charge transfer. So here's a look at both of the atomistic models that we'll be looking at the dynamics for. So the model on the left has the dye molecule oriented vertically above the perovskite thin film. So it has not a lot of coupling because it doesn't get the pi-pi stacking for coupling to the perovskite. So this is a case of like a minimal interaction between the dye and the perovskite for through space. And for the thin film model, we explicitly blonde the methoxy groups to iodides on the surface to model a through space charge transfer. And you can see that the bond lengths are approximately 3.3, 3.5 angstroms for each, and that both of the molecules are about 6 angstroms to 7 angstroms away from the surface of the perovskite. So they should be provide similar results to one another for spatial locality anyway. So on the left is an image showing the typical way that a charge showing hole transfer in these materials. So on the left we have the band diagram for a perovskite material, on the right for the dye and /DML molecule. So the first step would be optical absorption of light that creates a photoexcited pairs of an electron in the conduction band and the hole in the valence band that occupy 2 specific states. And then pretty soon after that, due to electron-phonon coupling, the excited charges will relax towards the band edges. And then since the dye HOMO is larger than the perovskite HOMO, we expect that the hole should transfer to the dye, creating spatial separation and creating hole transfer. So for the models, so for the computations that we do, we're going to define the HOMO of the dye as a successful hole transfer rate so that there are no hot holes extracted. It would be all the excited state energy would be lost to thermal bonds. And then just to illustrate these charge transfer states, we show the orbitals to the left, and then on the right is the density of states for each assembly. So for the top one is a thin film in the dye, where you see that the electron density is partitioned between the perovskite, which is the yeah, I was just waiting for if there was a question occurring here. So yeah, the blue states represent the electron density of the dye, and the red represents electron density of the perovskite. And then the filled bands represent occupied states, and then the unfilled bands represent the unoccupied states. And for both, we can see that the HOMO of the dye is greater than the perovskite as expected. So we'd expect the orbitals to be located on the dyes, which is shown in the left 2 images. And then one important difference between them is that for the thin film with the linker groups, it's got extra electron density located around the valence band edge of the perovskite thin film, which will be important later. So onto our electron dynamics. So we compute our electron dynamics by solving using density matrix formalism and solving the Redfield equations, which we break apart in between the Louisville superoperator and Redfield superoperator. And the Redfield operator provides dissipation, energy dissipation due to electron-phonon interactions. And then for each time step, we solve those equations, and they give energy occupations for each state. So for the top left figure that we have, it shows a time evolution of photoexcited energy states, where we have excitation from HOMO minus X to LUMO plus Y. And then the bright yellow bands indicate expectation values for electrons, and then the bright blue bands shows expectation energy values for holes, and then the green background is just the equilibrium energy of the ground state. And then it is computed in a logarithmic time, so -3. So on the bottom, -3 would be a femtosecond, 0 would be 1 picosecond, 1 represents 10 picoseconds, and so on. And then when the energy expectation values level out to the LUMO, we calculate rate constants from, I guess I didn't explain that. Explain the equations how we get rate constants. So basically we set up a dimensionless energy as shown in the equations below, and we assume that it's equal to a single decaying exponential. And then we can solve for the rate constant kh, which will provide the rate constant for the holes, which is shown to occur in the images below. And we define that kh as the hole transfer rate to the top of the valence band, or the HOMO orbital. And then on the right, it shows the spatial distribution of charges in the excited state, which is found by just projecting the orbitals onto the z-axis and then computing occupations through time. And we see that again, the bright orange bands correspond to electrons' occupations, and bright blue bands correspond to hole occupations. And then changes in those show changes in the electron density during time. And on the right shows, or the right of the image shows projections of the density onto the dye perovskite assembly. Oh, yeah, John?
No, I just had a quick question. So in the labeling on these axes, I mean, you have time, log 10, and then t over 1 picosecond. Is there a reason you have t over 1?
No. You're talking about my kh
I'm
equation?
just curious. Yeah, I'm just curious about the label of the x-axis in both the figures.
Per picosecond, time per picosecond.
I have a
Like t over 1.
contribution.
Oh, I see. So yes, normalized. So yeah, it's normalized to picoseconds. So 0 over 1 would be 0, or log of 0 over 1 would be 0. So that would correspond to 1 picosecond.
Okay.
So it's argument of logarithm is set up to be dimensionless. Makes sense?
Yeah, no, that makes sense. Yeah.
So then, in the next slide, we'll look at hot hole relaxation in these systems. So on the right-hand side figure, we show the time evolution of the energy expectation values for the systems, and below them the density of states. So for the thin film dye assembly, the excitation that we chose was HOMO -2 to +10. We chose that one based off oscillator strings, which represent the most probable transitions to occur. And then for the thin film DML assembly, it was an excitation from HOMO -10 to LUMO +5. And we see that for both of them that there is a multi-exponential decay, where for the dye system, it decays from HOMO -2 to HOMO -1, then from HOMO -1 to HOMO. And then for the thin film DML system, it decays from HOMO -10 to HOMO -1, and then from HOMO -1 to HOMO, with two different rate constants. So we can explain why there's multi-exponential decay in both these systems due to the energy gap, as shown in the density of states. So you can see between the HOMO and HOMO -1 states, there's a 0.72 gap for the dye system and a 0.81 for the DML system. And if you consider our non-adiabatic couplings that mix the two states, that's using the Feynman-Hellman theorem, you can show that it's proportional to the energy difference between both the transitions. So if we have a big energy gap, it's going to provide a big energy gap is going to decrease our rates compared to the other transitions, which are almost continuous. So that's why we have a subgap between the HOMO -1 and the HOMO states for both of these systems. I guess I forgot to mention that using the non-adiabatic couplings, our transition rates can be computed using the Fermi golden rule. So we put the non-adiabatic couplings into the Fermi golden rule, as shown on the bottom right, and then we can use that to represent non-adiabatic transitions in these systems. And then on the left is just a more conventional illustration showing the rates and the times between each of the transitions. So we can see for the HOMO -2 to HOMO -1, for the dye system, it takes about 11 picoseconds. And then for the HOMO -10 to HOMO -1 transition in the DML takes about 1 picosecond. So they're about roughly, there's an order of magnitude difference, but nothing dramatic between them. But we see for the HOMO -1 to HOMO, there's a big difference between the two states. And just to make it really explicitly clear, that for the dye, it takes 2.79 nanoseconds for the state, for the HOMO -1 to HOMO transition, where for the through bond transition, it only takes about 8 picoseconds.
So it's 3 orders.
Yeah, so there's 3 orders of magnitude difference between them, which can't be explained due to the energy gap from the density of states, because it's like, if you take the ratio of their differences, it's about 1.5, so it's not going to be 3 orders of magnitude difference. So to explain where that comes from, we look at the electron density for each of the systems, and specifically look at the effect of the bonding system compared to the non-bonding system. So for the left system, which is a thin film in the dye, we see from plotting the orbitals HOMO -2, HOMO -1, and HOMO, that the populated HOMO -2 state is located on the perovskite, and then when it relaxes to the HOMO -1 after about 10 picoseconds, it's located on the perovskite, where the HOMO of the system is on the dye. So there's very little orbital or electronic interaction between those, because if you consider, or if you approximate the orbitals as exponential decaying in space, that usually, like a rough estimate is that the orbitals will decay about maybe an angstrom to 30% of their values, about an angstrom away from the surface. And then they're pretty far apart, so you expect a little overlap between the two states. And then from our Fermi golden rule, we see that the rates are directly proportional to the square of their overlap. So if there's very little overlap, you'd expect there to be the rates to be very slow. Whereas for our bonded system, we see that for the HOMO -10 to HOMO -5, they're all located on the perovskite. But then for transitions closer to the HOMO, or higher in energy in the valence band, we see that we start to get electron density that's delocalized over the perovskite and the methoxy linker group. And you can see that from the density of states that the methoxy linker electron density is going to start to be degenerate with the perovskite. Someone ping out. Anyway, so between the HOMO -3 and HOMO -4 states, there's a link between the perovskite electron density and the linker density. And then once we get to the HOMO -1 and HOMO -2 states, they're entirely localized on the linker groups and the corresponding benzene rings for both of them. So there's a link between these two transitions, and then since these are located directly onto the perovskite, that there's going to be a lot of overlap between a HOMO -1 and HOMO state, which will correspond to a lot quicker transition rates. So we believe that to be the reason why for the through space bonds, it takes about 2 nanoseconds nanosecond order magnitude for non-adiabatic transitions to that state, while for the bonded state, there's a lot of electronic overlap between them, which will correspond to picosecond transitions. And then this is just more work that I have to do to convince the audience how well our models correspond to experiment. So just from looking at the literature broadly, there's a wide range of reported listings, which correspond kind of nicely to my computed results, or our computed results. So the fast whole transfer would correspond to about a picosecond rates, or time frame, where a long whole transition would be about nanoseconds, which is we get both to appear in our simulations. So my hypothesis is that the through space with very little electronic coupling between the dye and the perovskite would correspond to experiments where there was poor, experimental, setup of the perovskite in the dye. So they would call it bad pore filling for experimentalists. So there's not direct contact between the dye and the perovskite. So they're only spatially close, but there's no electronic overlap. Where the through bond pathways correspond to optimized interfacial dynamics between the dye and the perovskite. But I have to look through the literature more specifically and look for systems that correspond to my setups, because I don't know, the most direct result would be the perovskites that they don't have the TiO2, but they have the scaffolding, insulated scaffolding. So the electron's just located on the perovskite, and then there's only a hole transfer that occurs. But and I've also seen in some of the articles that the resolution ability of the instruments they use is kind of limited. So I have to look specifically on that as well. So just to recap for what has been covered in this presentation. So the two big things to look for is the large energy offset between the perovskite and the dye is going to just slow down the whole transfer process, just strictly due to the energy gap between them. And that the through space pathway will have minimal overlap, which corresponds to long pull transfer rates, while the through bond pathway provides bridging, which will correspond to very fast picosecond transfers. And that would be the presentation.
Okay, let's thank Aaron. So perfect timing, 18 minutes and 2 minutes for the questions.
Oh, nice.
You've misspelled the word through quite a few times, so be careful with that.
Yeah, that's something I do a lot.
And your second slide that happened to. So.
Yeah, make notes of it and I'll look for it.
John, did you have?
Oh, this is probably an easy question. So in one of the first couple slides, we were talking about different varying level of surface coupling depending on dimensionality.
Mm-hmm.
So is that just the coupling between the dye linker and the surface itself, or the coupling like in terms of like adiabatic coupling, or could you define that more specifically?
So one way to look at it is if you just have like per amount of perovskite you have a lot more surface area. And since this is a surface area limited reaction, well not reaction, but surface area limited process, that you have more at-bats to get charge transfer between them, so you can maximize the amount of charge you can pull out. So that's one way to look at it. Then there's also a thought that with decreased dimensionality, you have higher surface energy, so that will lead to increased electronic coupling as well. And I've seen some papers where they compute like a nanowire, or the interactions between like a metallic or semiconducting nanowire and an electrode. It provides a higher electronic coupling, like per same distance of the bulk material. Mm-hmm.
So I know last week I made a comment that I thought you had a little too much introduction.
Mm-hmm.
I think this week it seems like you cut out all of it. You didn't have much like useful in the real world. Did you talk about that? I don't know. I might have jumped for a second.
So I don't explicitly mention it in words in the presentation. Like I mentioned that spirometad's a popular whole transfer material, is shown to be the most efficient, and that's what we're using to model or base our dye models off of. So that'd be one introductory piece I tried to slide in. And then also the experimental, or comparisons to the experiment, which would be like, you would normally do that like first if you're doing a more formal presentation. But those are two places that I put it in.
I just wanted to make sure you felt like there was a happy medium between them.
Well, it's really up to the audience for that.
More questions? Adam, Yulun? If no questions, let's thank Aaron once again.
No question.
Good. And John, would you like to present your work?
I can do that.
Excellent, thank you.
So can you see it on the screen?
You can.
Okay, perfect. All right, well, I am kind of following up behind Aaron in terms of discussing the lead halide perovskite material, but moving a little bit away from charge transfer between a type of charge carrier transport layer. A single lead vacancy can have so just, a really brief outline, and I might cut this out for the talk, but just a little short introduction and then go over the methodology, and then look at what role the lead vacancy plays in the electronic structure, and then what role it has in terms of directing dynamics and also for both molecular and electron dynamics. So just as the brief introduction, lead halide perovskites have become very popular with their low-cost, easy synthesis, and high efficiency in terms of photovoltaics. And so something of interest are the actual photophysics and how they relate to specific molecular motions within the material. Now, the synthesis of the material isn't perfected, so during production, it's easy to create defects within the material of different kinds, but also once the material is put into a device or out into the field, there can be some typical sort of type of breakdown that can also cause these types of deficiencies. And so we're interested in what role a single lead vacancy can have within a bulk material. And something else we're going to highlight a little bit is there a role of an IV molecule formation dependent on this lead vacancy, and how can that direct any of the dynamic processes? So Aaron covered most of the methodology in his talk, and so I don't know if I'll spend as much time because I do want to have a little bit of discussion once we get towards the results. And I'm guessing you probably have a slightly different version of the talk in front of you versus what I'll be presenting. But just kind of a brief outline of what we'll look at with the methodology is we'll start with looking at the ground state electronic structure. So taking these types of this cubic bulk system of this lead halide perovskite, looking at the electronics with and without a lead vacancy introduced into the material, but then also what happens when we start adding multiple charges into the system to have a charge defect system. And so through that, we'll be interested in the molecular dynamics, and so we'll run heating and molecular dynamic simulations, but then also using non-adiabatic couplings and a reduced matrix formalism within Redfield for types of electron phonon interactions and looking at dissipated energy of photovoltaic transitions. And so these are two equations that you saw earlier in terms of scaling the temperature and accruing the velocities to get to an ambient temperature which we want to study, and implementing those as input for the dynamics. And then going through the dynamics, being able to look at the electronic structure as a function of the atomic positions and how it changes from time step to time step to try and account for the atomic motion, what role it plays in migrating photoexcited charges within the material. And so once we have these types of non-adiabatic couplings determined between the time steps, we put them into a Redfield tensor which provides the transition probabilities between individual states, which is one portion of the overall equation for motion electronic degrees of freedom. And so the Redfield portion coupled with the Liouville can allow us to study this type of time-independent density matrix. And so starting from some initial excitation, which we generally take from strongest oscillator strengths within the ground state, we move an electronic charge from one state to another, and then follow the energies expectation value as a function of time, and fitting this energy with a single exponential to determine a rate of non-radiative relaxation for that event. So going from there, we move into some of the results based on these types of methods. And so the ground state density of states is a good place to begin. So for this type of system, once we create a lead vacancy and introduce an additional charge, it's going to create an open shell type spin system. And so it's easier to well, it necessitates spin polarized calculations. In order to be congruent throughout all of them, we need to do spin polarized calculations for all of the systems that we're interested in. And so there's three images here. One is the perfect no defect system on the left. And you can see that there is a red on top and blue on the bottom, separating spin up and spin down components to the density of states. The filled is the occupied, the unfilled is the unoccupied. And so with the left and middle portions, you can see that they're symmetrical on top and bottom, meaning that, well, and they should be because they were, well, there should be no mismatch of spin up and down electrons in the system because there's an even number. Now, the main difference between the middle and left is the creation of this lead vacancy within the bulk material. And so what I want to highlight here is
John?
in between, yes.
Which slide are you at?
Slide 9. Oh. Sorry. I was clicking on my PowerPoint on my screen and not the arrows on the presentation. Sorry. All right. Are we up to density of states?
Yeah, well, I think we were following, right? We were watching on our slides.
Oh, I'm there. Okay. Sorry. Yeah, I gotta remember to click
it
that
started
instead.
diverging too far.
Yeah, no, that's fine. I completely forgotten that I needed to click that instead of my PowerPoint. Okay, so the main difference between the middle density of states plot and the left one is the creation of this lead vacancy. And so what I said was I wanted to highlight this small unoccupied state that resides within the initial band gap of the perfect system. And there's also a tailing off at the valence band edge that you can see for this lead vacancy state. Now, the other important thing or system that we were looking at here is once we created this lead vacancy, we're adding an additional electron to the system, creating an open shell spin state. And so now we can see that the spin up and spin down components in the right density of states figure are no longer symmetrical. What you can see is for the beta or spin down in blue is there's a small unoccupied state created just above the valence band for the system. And so now we have uneven types of states, which can result in different relaxation pathways and maybe produce some different type of mechanism for facilitating any type of relaxation process, whether it be non-radiative or radiative or any combination of, or any type of recombination possible. And so going forward from this, outside of the density of states, we're also interested in the optics of the material itself. And so what's plotted here are, again, the density of states on the left, just more in line form. And for the top, it's the lead vacancy neutral state. And on the bottom, it is the lead vacancy with the additional charge. And so what you can see is that the absorption, which is the top right plot, you can see that there's this creation of an absorption band somewhere around 600, a little over 600. And so that's due to this new additional state within the original band gap. Now for the spin polarized system on the bottom, you can see that there's a additional state more or less produced by the spin down component at about 1100 nanometers. And so that's the very shallow state produced by this extra electron being injected into the system. And so there's both a combination of the up and down for a total absorption spectrum, but also how it breaks down into the two constituent components. It's important to note that we're taking them individually and for right now, there's no type of cross-coupling between the two spins within the system. Now, what's shown on on the right are partial charge densities for the HOMO and LUMO. I don't know, you probably can't see my mouse pointer, but for these bulk systems, if you imagine in the middle of this material piece that I'm showing, and then just up and to the right a little bit is where the lead is taken out of the middle of the material. And so you can see that a lot of the charge density for these systems is localized near this type of lead vacancy in the material. So going from the ground state to the heating molecular dynamics, trying to provide updated coordinates in some type of ambient room temperature condition that would resemble experiment, what we're able to do is look at how the electronic energies of each Computational orbital are changed as the atomic positions are updated according to this dynamic trajectory. So what's shown on the screen here are 4 different trajectories. On the very left, there is the energy fluctuations for the lead vacancy with no charge. And then secondly, there are the spin up and spin down fluctuations for the lead vacancy with 1 charge.
John?
And then, yes.
For the very first image, can you indicate later in this panel where is HOMO and LUMO?
Yeah. So
tell it right now by words.
Yeah, I was going to verbally go over that. Okay. So we'll just focus on the very first left image here, and then the rest of it will follow. So one of the interesting things that we're trying to figure out with the system is when I showed you the density of states for this lead vacancy system, so it'd be the middle density of states, there was this generation of an additional state within the band gap material. Okay. And after the heating simulation, and then at the beginning of this molecular dynamic simulation, so you'll see where the states start below -6 eV. So the HOMO and LUMO are actually both located at like -6.1, very close to that. And so band gap itself has more or less closed, but there's still this extra state localized, negative about 4.7. And so there's a restructuring going on even during the heating simulation away from what this ground state electronic structure looks like. And so then propagating along this molecular dynamic trajectory, you can see that this state that's more or less inside the subgap goes way up top and more or less forms up into that upper band. Yes?
Is it right that LUMO near valence band can be interpreted as p-doped semiconductor? Okay, good.
Yes. Yep. And so a lot of, a number of the literature results also go forward in discussing this creation of kind of like a p-doped unoccupied state that's just above the valence band itself. And so in this term, we're suddenly interested in what's causing these huge fluctuations in these Computational orbital energies in terms of molecular motion. So I'll get to that a little bit later. But the other important thing to know in that first left-hand plot is once you get to about 400, you can see that the top of this valence band, which would be the LUMO, this blue line, jumps up quite a bit in energy, almost to about -5 eV. And so I'm still trying to decipher where that's coming from, but we think it may or may not be related to the formation of some type of I2 molecule itself. So then the charged system, which would be the second column for alpha and beta, the alpha looks fairly benign. There's no real huge subgap or anything. With the beta, you see that at the more or less towards the top of the valence band, there is one state a little bit higher than the others that comes back down. And that's more or less expected as the spin polarized system showed that there was an unoccupied state close to the edge of the valence band for the spin down system. Now, a second system, which is relatively new, is this 2- dianion system. And so with 2 additional electrons, there's 2 different configurations. One is a singlet where they both populate the same, and so spin polarized calculations are needed, but then also a triplet state where they both populate 2 individual extra electronic states. And so with the singlet, you can see that again, there's this energy state that starts up in the more or less the subgap, but now with 2 additional electrons, it goes down instead of up. And so since the couplings are running through the systems, hopefully we'll find something out in the next few days or whenever they're ready about what might be driving that. And then with the triplet form, it more or less looks similar to that of the -1 lead vacancy system, where the beta does have a little bit higher energy, comes from orbital above the valence band that drops back down close to that. So there's definitely a distinct difference in how the different energy levels can be directed dependent on how many charges or what number of electronic states could be filled. So is there a commonality between just the lead vacancy neutral system and the dianion singlet that results in this energy state being pushed down versus it going up to the top of the subgap? All right. And so since the neutral system is one we have the data sets for, we're interested into why some of these fluctuations were so irregular compared to, more or less the standard smaller fluctuations but maintaining relatively the same energy. And so on this slide, I'm showing the HOMO and LUMO and then the LUMO +1. And so the LUMO +1 was a state that it started more or less in this subgap and jumped way up. But there's also, well, just showing again that the density is also localized for the majority of, well, the HOMO and LUMO around this lead vacancy, but then also for this LUMO +1, it's more or less in line. So thinking for one back, and not exactly localized right around the vacancy, it's more towards, pushed just a little bit outside towards the adjacent lead type atoms. And so the table here is showing what the energy values were in the ground state, just representing the density of states, but also how much they change during the heating simulation, so from the ground state to the beginning of the dynamic simulation. So you have the HOMO and LUMO both going very close to this -6.07, -6.06, and then having this LUMO +1 drop to the middle of this subgap, almost replacing the initial LUMO level itself. And so one of the things that's happening in this dynamic trajectory that isn't seen in any of the others is the formation of this IG molecule. And so this is a PDF. On the left, you'll see the whole structure. There's actually a video that goes with it, but that's not going to play for you. But then the other 3 figures are snapshots, and within the red oval on each of the systems is where this iodide formation is occurring. So at time of 292 femtoseconds, what begins is there's a full connection between a lead, an iodine, second iodine, and the second lead. So it's more or less all interconnected. At 359 femtoseconds, one of the lead iodine bonds breaks, and then at 475 femtoseconds, the second lead iodine breaks, and so now you have a free-form I2 molecule within the system. And so Okay, the next slide is also a video. So you're going to see the initial radial distribution function for iodine itself. If I was to click play for you, what you'd see is the main peak localized, just over 4, more or less kind of shift a little bit, become more asymmetric, and then you would see this small peak going down towards 2 come out, and so it oscillates back and forth somewhere between 2.4 and 2.8. And so the interatomic distance for an I2 molecule is about 2.65, give or take a little bit. And so it shows this peak forming and then oscillating up for the remainder of the system. And so I'm trying to identify a specific time period in which this I2 plays a major role in the dynamics themselves. Now, so that was just molecular dynamics based on classical calculations. And so the real interest lies in what role do these fluctuating energies of states have on the electron dynamics, so the photoexcited processes. So on here, what I'm showing are the Redfield tensors for the perfect system, the lead vacancy neutral system, and then the spin up and down for the charge system. And so this can give us a look at the transition probability between individual states, where the probability is higher for states closer in energy, which is why they're more or less located on the diagonals. But we can also try to look at relative intensities along the diagonal between the different systems and electronics configurations to see if there's anything that can try and help us moving forward. So between the perfect and the neutral, the creation of this lead vacancy, it almost looks like it increases the transition probability because the total scale of the intensity of these peaks doubles with the creation of this lead vacancy. But the second thing is also right in the middle of the plot is more or less the homo-to-homo or homo-to-homo and lumo-to-lumo transitions, which will be 0. And you can see that the relative intensity for the neutral within the conduction band has more or less a yellow and orange peak that are larger than the rest, whereas with the perfect system, it's more uniform. So there's a different coupling with the addition of these states close to the edges of the gap that are playing a strong role in that in the perfect system, which is what we would expect with new reaction relaxation pathways being opened up with the creation of this state. For the spin up and down systems, you can see that for the spin down, the intensity of the transitions at the edge of the valence band, so in the green, are less than that of the spin up system. And there's also varying intensity within the conduction band of the red peaks, showing specific transitions for this could be a little bit more interesting. And with the spin down system, we're expecting this unoccupied state very close to the edge of the valence band taking a large part. And so to look at the time scales that can come from strong excitations in the system, I took the transition with the strongest oscillator strength for each of those systems as examples to provide and just look at some of the relative differences between them. So with the perfect system, we're looking at a HOMO minus 19 to a LUMO plus 10 transition. And so here, the electron relaxation is somewhat close to just under 4 picoseconds, whereas for the whole relaxation, it's just under 1 picosecond. So not, well, so I would say they're relatively scalable to experimental results, but the charge carrier lifetime, the difference between the electron and hole lifetime isn't very big, which isn't necessarily what you might want for collection of the charges. Now, when moving to the neutral, with the addition of this lead vacancy, you can see that the whole lifetime is relatively similar to that of the perfect system, but the the electron lifetime is extended out close to somewhere around 75 picoseconds. So you have a much longer lived charge carrier lifetime just with the creation of this lead vacancy. And then moving towards the spin up and spin down with the relative similarities between the charge up and perfect density of states and also the charge down and neutral density of states, we would expect them to have similar rates and lifetimes of charge carriers, and indeed that is what we see, where the charge up has relatively small charge carrier lifetime, whereas for the charge down with this additional beta state, the lifetime is extended and there's a much more drastic change between the two charge carriers. And so with these types of results, with the extended lifetimes of these charge carriers, if it's connected to some type of electrode or transport material, having them separated for much longer allows for a higher collection efficiency, theoretically. But it can also enhance, if you can collect them before they drop down in energy, allow for a higher photo voltage or more energy to be extracted from this hot carrier before it cools or loses all its energy to thermal vibration. Now, the next slide is more or less just looking at the trending of the rates. So I listed here, a number of the highest oscillator strength transitions, but from the figure itself, it shows that there's a relative trend of the whole relaxations being much slower than that of the electrons, and also that there is some type of with a single exponential or needing some type of secondary look for multi-integral rate calculation, which is currently ongoing, and I know Aaron was looking at something about that as well. Now, that's all well and good for photovoltaics. In terms of optoelectronics, another useful portion is the photoluminescence, and so the ability to look at the relative rates of radiative and non-radiative portions in determining quantum yields within the systems can also provide a picture of how good these materials might be for other types of applications such as lasing. But we're also interested in what does this lead vacancy do to impact these types of quantum yields themselves. And so with the neutral and the spin down having similar density of states or electronic structures, we assume that the quantum yields might be similar, and indeed they're very low quantum yields, whereas the spin up doesn't have any additional defect state put into it, and the quantum yield is close to 45. And so the neutral, or the perfect system isn't on here, and I need to add that when we're done with this. So kind of in conclusion, we talked about the role of what a lead vacancy can do to the electronic structure of both methylammonium lead iodide system, and also how that can affect relative photoluminescence and non-radiative relaxation processes in the material. So with this additional state that can be created by lead vacancy, there's a chance for new relaxation processes and pathways available, while also reducing the quantum yield of the photoluminescence within the bulk material. And so one of the important things was being able to apply the spin polarized methodology to the system and account for both of the spins and what this might do, but also looking at how the charge of the system can direct a possible, molecular iodine formation, because it's only seen in a neutral system, whereas once you start adding charge, there's no longer the formation of this I2 molecule. And so with that, I think I will say thank you, and I have a couple other plus slides for discussion, but I will stop there.
Okay, well, thank you, John. Any observations, comments, questions?
Hey, John.
Yes.
I believe on slide 6 there is something that needs to be corrected.
Okay.
I apologize in advance if I'm incorrect.
No, that's fine. I gotta remember to change it on the other screen. Yep.
So I believe on the pairs of black arrows on the right side, the HIJ should be VIJ.
Yeah, if to be congruent with the equations, yes, that would be correct.
I made the same mistake in my presentation.
Right. I mean, the image itself comes from their paper, and that's how they had it labeled.
Okay.
But, so yeah, so there's there's a difference between the picture and how I labeled it, but I'll make a comment with that, but it's the same.
Okay.
Thank you.
Dane, you have a question?
Yulun's gonna do something.
Oh, okay.
Go ahead, Yulun.
Maybe you can come closer to the microphone.
I guess my question is about the quantum yield. So how did you calculate the quantum yield?
Right. So for the quantum yield itself, it's the ratio of the radiative versus the sum of the radiative and non-radiative portions. So the radiative rates are calculated through the Einstein coefficient using the oscillator strengths of the ground state structure, and then the non-radiative rates come from our dynamics calculations, and so that's where the rates come from, and that's what I'm using for the quantum yield.
Okay.
I think one of the very last slides I have. So here's where the radiative lifetimes come from. So that's just the A21 is the Einstein coefficient, and then flipping it to the lifetime, but getting the rate out using the oscillator strength, and then using those two rates.
Okay.
You have questions here?
Yeah, I got a question for you, John. So if you go to slide 16, that one. What one? 16, sorry, that's 17.
Is
with the electron dynamics?
Is it not showing?
It's there now.
Okay.
So your x-axis labels, or you have two different labels for your x-axis, and both of them differ from the ones that Aaron had. I was thinking maybe you guys could discuss why. Or...
Yeah, no, it's so I think so the one generally the way I do it is the figures on the left is generally how I show them, but I could easily switch them. So they should be congruent. I would agree that I need to change to them to be congruent, but also the way Aaron had it is probably more correct than what I show. So I should add that in.
Okay.
More questions or comments?
I guess I have a question. Yep, please. So, did you use 1,000 couplings, or for like for your energy fluctuations? It shows 1,000 time steps.
Yep. So yes, I did, and this is I have a couple questions because you did some of this where you did multiple integrals for getting rates. Is that correct?
Oh,
you looked at couplings for different systems and.
I guess honestly, I kind of ballparked it. I didn't explicitly change the code, so I just kind of lined it up with the logs because it works out nicely. Because if it's 0, it's going to be 1 or pretty close to 1. So I guess I didn't change it explicitly. I just kind of backhanded. But I guess my comment was.
Go ahead.
Right, I was just going to ask because since it looks like the rates that you got there around picoseconds, so I was just concerned that usually, if you didn't have enough couplings, if you tried to project that through further times, whether your results would be reliable. But since you got your rates up to about picoseconds, I guess it works out.
Yeah, I mean, it's so one of the things we've discussed is, so like if I go back to these plots of the fluctuations, right? I mean, so there's three very distinct regions in which the couplings could vary quite a bit. Where if you look at, say, 0 to 300, where that one Concha multiple goes way back up to the conduction band, and then when you look at, say, 700 to 1,000, you have this divergence of the top peak and the valence band that goes up. I mean, you're going to get, drastically different coupling regions between each of those states. And so one of the things that I've done is I've recalculated like the Renfield tensor, looking at specific sections of that. And one of the things that I did was once the iodine, the I2 molecule formed, looking at the coupling once it was formed versus before it was formed. And so this slide is for the strongest. Well, so I took the energy pop file from that specific time step where I started and at the end, and then the oscillating strength file for that time step. So this was the strongest transition. But even here, I mean, the whole relaxation is a little bit longer than the first iteration, but only because now the holes become more separated in the second half of the trajectory, rather than the first half. All those states are relatively packed together. And so I got to figure out a way to find a good balance between capturing what's actually going on with those segments of where the spacing is changing for the energy levels. So yeah, that's something I got to work out a little bit though.
I think it'd be helpful just to look at maybe one system specifically, because I mean, it's good work doing all four, but it's kind of hard to keep track between all of them and systems at one time.
Yeah, well, and that's why I think with the neutral system with this iodine is getting formed. I mean, that's definitely more interesting than some of the others where there's nothing else really happening in the dynamics. And so, but it could change once we get the couplings done for the doubly excited, the two anion state or trajectory. So, yeah, I'll try to keep that in perspective and focus on the one, and then maybe look at trending at the others as kind of a secondary thing.
So. 10 minutes over the time for the presentation. So you need to design how to squeeze and explain it principally. So please scan and send comments to John. And let's thank him once again. Yulun and Adams. Maybe Yulun will go first because it will be quicker, and then the whole time after will be dedicated to Adams' thesis.
Okay. We will attempt to share screens here.
Please.
Oh, that's not going to work. Okay. Can you guys hear?
We can hear, but we do not see your slides.
Now?
Not yet. Not yet. There should be share the content. John, can you explain if?
Just a sec. I'm installing an extension.
There you go. Okay. Yes, it works. We are waiting for connection to re-establish. It is a little gray. Our screen is gray.
Can you hear us now?
We can hear you now.
Okay, sorry about that.
Not a problem. It was kind of intermittent.
Can you see it now?
Yes, but we see it in gray color. Or it is no, it is color. So you think storm affects the...
I saw a video of the grapefruit-sized hail smashing into these cars and over in front of.
Okay, well, that's not working. It keeps crashing our connection.
Oh, I see Wendy there. Hi, Wendy. How are you? Oh, good, good.
All right, so we're going to try.
Oh, if nothing works, I can flip your slides and project them here, and then you guys will just verbalize what you're showing. It's not
There's no way to really do that. Okay. All right, I'll have to email you guys my newest version.
Okay.
My slide.
But can we start with... Oh, there is something new.
Oh, well, Yulun's got...
We can go for... While you are sending, we can go and hear for Yulun's presentation.
Right. Yulun, he has your most recent version. Okay. We can't connect. No, it doesn't connect. The wire Ethernet's broken. Or wired. Yeah. Okay. So if you want to pull up Yulun's slides.
Yes, and I can share them.
Why here?
I will have limited ability to write on slides, but okay, I'm ready to flip the slides.
Okay. Just one moment. Okay, I've got my slides sent to you now. Okay. And we can see Yulun's slides on here.
Okay. Is Yulun ready?
Okay, so my topic is the photofabrication of gas-phase molecules, experiment and computational modeling. Can we go to the next slide? Okay, so here is a brief overview of physics. Our group is interested in fabrication of gas-phase precursors. This includes small organic molecules and large metal-organic complexes. So we have two methods to study the photofermentation reaction. So experimentally, we can use photoionization time-of-flight mass spectrometry to get the mass spectrum of the gas phase precursor. And there are many features in the mass spectrum. Based on these features, we can propose the photofermentation mechanism. And then computationally, we develop a DFT-based time-dependent excited state molecular dynamics to simulate the photofermentation reaction. And in TSESMD trajectories, there are many dissociation events. And based on these events, we can identify the photofermentation mechanisms. Next one. So here is a setup of experimental photoionization time-of-flight mass spectrometer. So it's pretty much the standard QF instrument. So at the bottom, we have the diffusion pump, and at the top, we have the turbo pump. So in the middle, we have the TOF chamber, and we have the sample holder. So the laser we are using is a neodymium young laser. Although the dissociation pattern is wavelength dependent, we usually find that the 266 nanometer wavelength excitation gives us a better mass spectrum. And the pressure in the TOF chamber is about 10 raised to the power of -4 millitorr. And the pressure in the sample holder is 10 millitorr. So at these conditions, we can make sure there is no collision between molecules. Next one. Okay, so here I'm going to briefly talk about the DFT-based time-dependent excited state molecular dynamics. So the name we are using is a little bit awkward because any molecular dynamics is time-dependent. But here we use this name in order to emphasize that our molecular dynamics has time-dependent electronic configurations. So our method is different from ground-state molecular dynamics, different from fixed excited state molecular dynamics, and non-adiabatic molecular dynamics. So in TSESMD simulations, the electrons are hopping between excited state and ground state. So first, electrons are promoted from ground state to excited state and stay here for a short period of time. And then it just relaxed from excited state back to ground state. And it stayed here for another short period of time. So this is called a Rabi cycle. And the TSESMD trajectories has many Rabi cycles. And during these Rabi cycles, the system accumulates kinetic energy in order to overcome the dissociation barrier and finally leading to photodissociation. So there are many information we can get from TSESMD simulations. For example, we can get the activation energy, we can get the branching ratio, we can even get the mass spectrum from TSESMD trajectories. So next slide. So here I'm going to talk about some photofragmentation for lens-side cyclopentadiene complexes. So why we are interested in lens-side cyclopentadiene complexes? So the first reason is it is very common complexes for organometallic chemistry. Second is this kind of precursor can be used as precursors for lens-side for laser-assisted metal organic chemical vapor deposition technique to prepare lens-side oxide thin films. And the lens-side oxide thin films have many applications, for example, as beta oxides, as optical amplifiers, as protective coatings, and solid fuel cells. And so one of the drawbacks by using lens-side cyclopentadiene complexes to prepare lens-side oxide thin film is carbon contamination. So through the investigation of photofragmentation of this specific compound, we want to find out the origin of this carbon contamination, and we want to avoid this kind of contamination in future. Next one. Yeah, so here I show the mass spectra of lens-side isopropyl cyclopentadiene complexes. So in the mass spectra, the dominant peak is lens-side bimetal. We also observe the parent peak, the bis-complex peak, and the monocomplex peak. So basically, there are two major dissociation pathways. The first one is called anti-ligand injection. So the isotope ligand is sequentially injecting metal on the metal, and by three initial steps, you can have the dimetal. So, and click on the screen. Yeah, so actually, our simulation agreeing very well with the proposed mechanism based on mass spectrum. So here we start our simulation with geometry optimized model, and we can see all three ICP ligands are bound to the metal. And as time goes by, we can see the first ligand is ejected, and then the second ligand is ejected, and finally all three ligands are ejected. Yeah, and go to next slide. So the other photofragmentation pathway is called ligand cracking. And here I show the expanded mass spectra in the low mass regime. And actually, the ligand cracking pathway is very complicated. I'm not going to focus on it. But basically, we have two types of species in the mass spectrum. We have species with even number of hydrogens, and we have species with odd number of hydrogens. So species with odd number of hydrogens come from left side ICP1, while species with even number of hydrogens come from left side ICP minus hydrogen. And we propose this left side ICP minus hydrogen is derived from left side ICP2 complex. So next. So here is the proposed mechanism. So the ejected ICP ligand extracts one hydrogen from the ligand remains bound so that it can live as a closed shell molecule HICP. And finally, we can get this left side ICP minus hydrogen. And actually, our simulation reproduces this process as well. So start with the geometry optimized model. Yeah, and the next. Yeah, at this time, we can see a hydrogen atom is ejected from the top ICP ligand. And as time goes by, this hydrogen is forming a bridge between metal and the ICP at the lower left. And later on, we can see the hydrogen migration is complete. And we have a complete HICP molecule, and this HICP molecule is ejected, and it is fairly stable during the rest of simulation. And in the top, we have the ICP minus hydrogen. Next slide. So far, we have applied spin-restricted time-dependent excited state molecular dynamics to left side cyclopentadienol complexes. So actually, we can still improve our method. So we can simply include the spin in TSESMD simulations. So here I'm going to briefly talk about spin on restricted TSESMD simulations. So the modeling is based on one electron quantum equations. By solving these equations, we can get orbital energy and quantum orbitals. The time evolution of electronic degrees of freedom can be calculated by solving the equation of motion based on the equation I listed here. So the first term is a Fock matrix. The second term is a density operator. And the third term is just dissipative transitions. And the Fock matrix has three components. The first one is the ground state Fock matrix. The second one is non-adiabatic coupling. The third one is light-to-matter interaction. And actually, this light-to-matter interaction term is time-dependent. But by applying some approximations, we can treat it as time-independent. And based on Rabi's theory, the Rabi frequency is related to transition dipole and the intensity of the electrical field. So the propagation of degree of freedom can be modeled by Rabi oscillations with hops between different states, and these hops can lead to a stepwise change of orbital occupation. So through these equations, we can get updated density, total density of electrons, and with the new density, we can update the interatomic forces, and with new forces, we can update the position of ions. Next slide. So here I'm going to show another example. So this time I'm going to apply spin unrestricted TSESMD to a new molecule, a tetradichromacy molecule. So why we are interested in this molecule? First, it's because this kind of molecule has many applications, and there are some experimental studies available for the fermentation of this molecule. However, the theoretical study is limited, and also because this molecule has very few atoms, so we can save lots of computational resources. So here I show the basic electronic structure of this molecule, and this time we consider two systems. So the first one is neutral TNM, the second one is TNM cation. As we can see, so for the neutral system, the spin alpha and spin beta component are the same, but for the charged species, spin alpha and spin beta are different. Next slide, please. So we apply spin unrestricted TSESMD to tetranitromethane, and then we can get the TSESMD trajectory. And then next, we want to build the energy diagram for the photofermentation reaction, so that we can get the activation energy for specific chemical reactions. However, in TSESMD trajectories, we get hot intermediates with excessive kinetic energy. So it is impossible to accurately estimate the activation energy based on these hot intermediates. So we have to apply a post-processing technique. So what we do is we apply single point energy calculation to the intermediates in order to artificially remove the kinetic energy. And after we finish this process, we can get the energy diagram on the right. So as we can see, the starting point is tetranitromethane molecule, and the final product is gas phase components. So we have 3 nitrogen dioxide molecules, and we have a carbon monoxide, and we have a nitrogen monoxide. And the activation energy for this reaction is about 4.1 electron volts. So, and actually this final product is very consistent with experimental findings. Next, please. So actually, we can extract the simulated mass spectrum from TSESMD simulations, and we can even compare with experimental mass spectrum. So next, please. Yeah, as we can see here, the simulated mass spectrum has some similarity with the experimental electron ionization mass spectrum. So the dominant peak is nitrogen dioxide. And so the red one is for the neutral system, and the blue and green one is for charged species. As we can see, the parent eye for the neutral system is stronger, but for the charged species, it is much weaker. So this tells us the cation is much easier to fragment than the neutral system. Yeah, that's all.
Okay, let's thank Yulun. And other questions?
Yes, I have one.
Aaron?
So on slide 6, you say that you for your transition from HOMO -2 to LUMO +11, you choose that one based on oscillator strength? Or that specific transition based on oscillator strength?
Actually, we have two considerations. The first one is this transition has to be a ligand to metal charge transfer transition. The second one is it should have relatively large oscillator stress.
Okay, so then is the oscillator strength like relatively constant in time, or does it decrease as it starts to fragment?
No, the oscillator stress is based on geometry optimized structure. So it is fixed. But in the trajectory of TSESMD simulations, I guess this oscillator stress should be different, should changes.
Ideally, one should monitor change of oscillator strengths and adjust excitations with time according to change of the oscillator strengths.
Okay.
But for simplicity, as an approximation of short times, one chooses the oscillator strengths of the relaxed geometry, which is not as further away from initial geometry we go, as worse this approximation is.
Right. But it's easily optimizable, like if you do an experiment.
Mm-hmm. More questions? If no, let's thank Yulun once again. And it will take me very brief to download the slides by Adam and go for